Alrighty, welcome back, folks. Let's go ahead and take a look at 61 through 65, the last questions here on 25M. I've been waiting for this one to show up, the toilet paper questions. They were quite popular back in the day and they can be kind of silly. So let's go ahead and see here. The thickness of a 4.5-inch square sheet of toilet paper is 152 micrometers. Now, the important thing here to remember is that micro means 10 to the negative 6. So instinctively, when I'm working with these types of numbers, I just change that prefix to the times 10 to the equivalent. They want us to find out how many sheets are on a roll if the outside diameter is 4 7/8 of an inch and the inside diameter is 1 3/4 of an inch. Man, I remember when the inner diameters were about an inch. Talk about shrinkflation. So how do we start solving this? Well, we want to make a model. It's going to be a donut. So donut areas are really neat because they help us solve a lot of problems like this. So we're going to, the donut area would be the area of this outer circle with a diameter of 4 7/8 inches minus the area of this inner circle, which would have a diameter of 1 3/4 of an inch. Now, why do we care about that area? Well, if we take that paper with a certain thickness, right, it's going to wrap around and spiral, and that thickness is going to add up over the distance. And so that thickness is what's going to give us that area. Now, one way we can think of this is length times perpendicular distance gives us area, and that's what's going to happen here. So that donut area is going to be the length of the toilet paper, all those sheets put together times their thickness. So if we want to find out how many sheets we're going to need, we need to get this total length. So we get the area of that donut, larger circle area minus inner circle area. And then we divide by the thickness of the paper, which is, I believe, 152 micrometers. So we're going to have to do some unit conversions to ensure that the micrometers cancel out. Now we just convert those to inches. So, what's the thought process, right? Get the donut area, subtract the two circle areas, get the length by dividing by the thickness. Then, once you have that total length, divide by the length of the sheet, and that's going to give you the number of sheets, and there we are. 62. 62 is an overflow problem. Thankfully, it's a manageable one. 874 to the 1000 times 874 to the 2000. That looks a little intimidating because we're used to doing overflow calculations with just one number. A number raised to a power. The good thing is because we have the same base here, we can apply a little convenient trick of bases. If I have x squared times x cubed, that's really x to the 5th. Right? Because it would be like x times x times x times x times x, or x times x times x times x times x, whatever, fine. Right? So the upside is we just add the powers. So this is the equivalent to saying 874 to the 3000. Then from there we do our typical overflow calculation. We take advantage of the logarithm trick to rewrite the exponent and the base. And so logarithm of the answer, a, is going to be 3000 times log of the base. When we evaluate that, that becomes this number here. So log of our answer is going to be this weird mixed number. Now the upside to this is if we take this expression and we multiply, or we raise 10 to this entire expression, so 10 to all this junk, the log's going to cancel out. Now the upside is that doesn't actually change the number, but it's changed how we've written it, which makes it convenient in rewriting this disgustingly large number that would normally give an overflow on the calculator. So when we tend to it, we get a back, and that's going to be 10 to the 8,824.534 and repeat whatever decimals. Now what we want to do here is we want to take this other part and write it as an integer part and a fractional part, because it turns out our answer is going to be 10 to the fractional part times 10 to the integer part. And the reason we do this is because, remember, we want to write all of our stuff in scientific notation with 3 significant digits. and then times 10 to the whatever exponent. Now, 10 to the fractional part is actually going to turn into a whole number, which becomes about 3.422. 10 to the whole part, or the integer part, is just what we want, so we're just going to rewrite that, and that just drops down. And so that's how we do that overflow. Oops. The next part. 2 tennis balls are thrown with an initial velocity of 48 miles per hour and caught 100 feet away. Immediately, I would convert the 48 miles per hour to feet per second, and that is a multiple of 22 over 15. So 48 times 22 divided by 15 is going to be in feet per second. Now, they tell us that one was thrown high into the air and the other one was thrown straight at a low angle to the catcher. And they ask, what is the positive difference in the maximum vertical height of the balls? Well, to do this question, see here, whoops, I'm in the wrong spot. We're going to need to do a little bit of projectile motion. Now, when we do this problem here, one thing to recognize is once we solve for one of the projectile angles, there are always two angles that we can launch a projectile that will get us there at the same location ideally. And those two angles are actually going to be complementary, or they add up to 90. So we'll use that in, part of our solution. Now they tell us that the balls travel a distance of 100 meters horizontally. And a lot of these questions lately have been solved using this expression. The maximum horizontal distance equals the launch velocity squared times sine of 2 times the launch angle divided by the acceleration due to gravity. Now here we're going to want to make sure that we have consistent units. For instance, the acceleration due to gravity is going to be 32.17 feet per second squared. And so we're going to want to make sure that our speed has units of feet and seconds in it, so feet per second. Okay. If this were in meters, then we would use 9.8 meters per second squared, and our speed would have to be in meters. Oops, I put the wrong units. Second squared. Okay. Alrighty. So we populate that in here, and so we get 100 is going to equal the velocity, 48 miles per hour converted to feet per second is 70.4. We square that times sine of 2 theta, all over 32.17. And so we get 20.23 from our solver as our angle. The other launch angle is going to be 60.76. Now, they want us to find the difference in the heights. So we're going to do two calculations for the maximum vertical distance. For the maximum vertical distance, the formula for that is the velocity squared times sine of the angle squared over 2g. These formulas look very similar. There's a v squared, there's a sine, but the twos kind of change spots. Now the way I remember this is for the horizontal distance, it's 2 times the angle, and the way I remember that is because if we're going horizontally, I guess there's that angle, and then that angle over here, so 2 of them. Now, from there, what I remember is, okay, y max, because the acceleration of the vertical distance is accelerated, there's a square there, and then because the 2 is not on the angle, it drops down to the g. I don't know if you care to remember it that way. It's terrible. That's not good explanations, and I hate memory devices, but it helps me out all the time. Alrighty, so we plug those numbers into this y calculation for the two angles, and then we subtract. Alrighty, let's go to 64. 64 gives us the shaded area of this triangle. Now, commonly, what we would want to do is take the total area of the square, subtract the 3 triangular areas, and then that would be the shaded area. But because it's a triangle, and everything is bound by the side lengths here, we may want to do Heron's formula. To do Heron's formula, we're going to need these 3 sides. To get these 3 sides, hopefully we recognize that, by golly, we can use Pythagorean theorem. Because this is going to be x for the unknown. This is x over 3, because it's a third point quantity squared. And we add those two numbers, and then we square root them, and then that becomes this side length. This side length over here is going to be 2/3. And we do the Pythagorean theorem again with 2/3 on both of these. And so because these are the same side length, we'll find out that this guy becomes square root of 2 times this side length. So that's square root of 2 times 2/3 times the side length. All that yapping can be confusing if I don't have any diagrams to help us. So let's go ahead and take a look here, right? So the first triangle, right? X over 3. You do all your Pythagorean theorem. That becomes square root of 10 over 9x, or a. For the second triangle, right, that's where I was talking about it was 2/3 a, 2/3 a. You do the Pythagorean theorem. That becomes 2/3 times square root of 2 times a for this part. The last triangle is actually the same thing as the first triangle, so it's going to have a similar area, a diagonal of 10 over 9 square rooted times a. Then we throw all that into Heron's formula, which has a semiperimeter times semiperimeter minus a times semiperimeter minus b times semiperimeter minus c. All of that square rooted gives us the area. So this is where having things programmed into your calculator is really handy. You just throw it in there. So all that area is going to equal 853. Put it into the solver. Solve for the side length A. Don't forget, S is the semiperimeter. The 3 sides added up divided by 2. And the 3 side lengths would be the diagonals here that we found for our triangle. Okay? Because again, Heron's formula uses the 3 sides and the semiperimeter with those sides. So it would be the semiperimeter there. Okay? Alrighty. Let's continue. Last question. 65 looks intimidating because it looks like none of the geometry really matches up, right? Like, oh man, this is a right triangle, but it doesn't quite extend right through anything. But we can take advantage of the distances involved making a right triangle and this concept of similar triangles. So the radius to this length here, 16.5 minus the radius, because again, this here is also the radius, and this whole distance here is 16.5. So 16.5 minus the radius gives us this distance from here to here. So this r over 16.5 minus r is to this height 12.9 minus r over r. So thankfully we can take advantage of those similar triangles to solve for that last one. Now I'm trying to see here if I happen to draw or have a better explanation of it, but it looks like I did not. I apologize. Yeah. Well, that's it for 2025 M. Thank you everybody. Have a good day.